Okay, section 518 is called dynamic braking and mechanical time constant. What we're going to do here is we're going to actually put some quantitative uh, analysis to this dynamic braking, and we'll be able to, since it's an exponential function, we can model it um, with, you know, the our knowledge of that area. And so it's interesting, and it's very similar to what you did when you looked at capacitors and inductors. It follows the exponential universal time constant curves, and we'll explore that in terms of dynamic braking. And what we'll end up doing, we can actually select a resistor to get the machine to stop at a particular time, which is an interesting thing to be able to do. And what I'll do too, I won't have time, of course, and I hope you don't need it. I'll do some remedial videos that I've got in stock, so to say, and I'll put that in the remediation folder in this module that we're working on. Okay, so as he tells us in 518, as the speed decreases exponentially with time, in regard to dynamic braking with a DC motor, we can speak of a mechanical time constant in much of the same way as we speak of an electrical time constant of a capacitor that discharges into a resistor. So that when I'm looking at this curve, this dynamic braking curve here, I can put some values on here. So what we're talking about is the exponential function e, and so if we were looking at this and we were modeling like we did capacitors and inductors, we would come up with the time constants. And after one time constant, the speed would be 36.8% of its initial value. Okay, so after one time constant, it would be at 36.8% of initial speed. Now, that is strictly speaking, to the universal time constant. We went, remember how we went through and we said after 5 time constants, it was either completely discharged or completely charged or whatever. But he says with machines, it's an easier thing to do to define something, a different time constant, and we call it this. And what it is a time constant that gives us 50% of the initial speed. So, that's what this figure 518 is showing us, that after this T sub O, the machine is at 50% of its initial speed. And I get, I guess that is a little easier to work with, and it makes a little more sense probably with electrical machines to define the time constant that way. And we can easily adapt this to our electrical machine, because what we'll do is we'll define this time constant as this number. And again, we're not going to derive things. That's not our purpose here. We're just going to take this and run with it. And so this, what we call half time constant, T sub O, is 0.693 times this universal time constant. Okay? So, if we took, this value, right, this, and so that's where, that's where that comes from. That's where those actual numbers come from. This value this conversion is actually given an equation number that we call 5.8. And then our textbook says we can prove that this mechanical time constant is given by this value. Okay, so let me write this down, and then we'll talk about it a little bit. Okay, so we've got this, and this ends up being equation 5.9. This is equation 5.9. And this is the time. This is the time, I switch colors here. This is the time for the motor speed to fall of 1/2 its previous value. So when I look at that, you know, after one of these, I'm at half. After another one of these, I'm half of the half. And after another one of these, I'm half of the half of the half. And I'm at that point. J is the moment of inertia of the rotating parts referred to the motor shaft. Okay, so that is a number that, you know, we would be given of the J number. The N sub 1 is the initial speed of the motor when the braking starts. The initial speed of the motor when the braking starts, and it's in RPMs. And P sub 1 is the initial power delivered to the motor, delivered by the motor to the braking resistor, and that's set up for dynamic braking. And 0.693 is a constant. It's the value of the log base E of 2, and that's where that comes from. So the equation is based upon the assumption that the braking effect is entirely due to the energy dissipated in the braking resistor. We know, though, that that's not all of the effect on the slowing motor. There's also friction and windage, and those are considered too. So what we would say is that the actual time would be less than this equation gives us, but you know, this would be the portion of this that we could easily quantify using these values. Okay, so let me stop there, and we'll call this part 1 of 5.18, and we'll work through example 5-6 and make that part 2 of this problem, where we'll actually work through a problem and do some calculations through there.